Hello friends, welcome to Conf 42. I'm Alex from Barbara, the Edge Computing Company, and today I'm going to be speaking about MLOps at the Edge. I would like to start with a very direct and very blunt statement. For us at Barbara, the cloud is broken. And you might be using the cloud a lot, probably. You might be loving it, especially if you are building these great models online, and you might be deploying them online. So you might be asking, hey, how come that a two-digit growing industry might be broken? So what's the problem with it? So why do you say that the cloud is broken? Well, I bring today 8 different reasons why we think here at Barbara that the cloud is broken. The first one is that it's too dependent on the internet. So if you're running a cloud service, you're obviously running all the workload somewhere else, not in your own infrastructure, not in your PC, not in your servers. You're doing it somewhere else. So you are relying on a good connection to perform anything that you want to do, right? So you depend too much on the availability of that connection, and that might be a problem for some applications. Secondly, there's a latency problem here. It doesn't matter how good your connection is. There is a round trip time of your petitions that go to the cloud and come back. So it takes a little bit of time, and that might be not good enough for certain applications, especially for real-time applications. So that round trip of the time that it takes for any data, any petition, anything to go to the cloud and come back might not be fast enough. You might have latency problems. Then there is also a problem of service availability, and this is related to the first one that I spoke about. Because you over-rely on the internet, then if there's a downtime on the service or if there's an interruption on the service, you're going to suffer. Your service is going to get interrupted as well because you are over-relying on the cloud. The number 4, there is a loss of control here because you don't own the infrastructure, which is great for some applications because obviously it will take a lot of money and effort to maintain those, but sometimes you might want to do things here and there. You might need to troubleshoot, to debug, and there's some situations where you're going to want to have that control of the infrastructure, that control of the underlying technology. So it might be difficult for you to optimize or to customize some services because you're not the owner of the infrastructure. So there is a loss of control that you need to take care of. Then there is a problem with cost. I mean, the cloud is some sort of a luxury many times, and also the cost is not easy to manage other times because they usually bill you based on the usage that you do, and usage is something that changes a lot depending on the needs of your application. That might be a problem, but also if you deal with an application that takes a lot of data, such as computer vision, for instance, which is a very data greedy sort of service, then you're going to run into trouble if you want to, upload all your video feeds to the cloud in order to process them there. So here, especially in data-intensive tasks, you have to take care of cloud costs because they can become a liability. Then on number 6, we have vendor lock-in, and many of these cloud tools, they usually impose you, they usually force you to use to do things their way, right? Because they are different across different vendors. There's not like a standard way of doing things. So chances are that you will have to adapt to the way of this or this other cloud. And then if you want to move vendors, if you want to change vendors, so say that you want to, leave AWS and move on to Google or move on to Azure, then chances are that you will have to reprogram to change many things in order to be able to use this new platform, right? So this sense of vendor lock-in, which makes it a little bit difficult to change providers. Then on number 7, there's always the problem of security and privacy. It doesn't matter how good your encryptions are, whether you use VPNs, whether you use whatever means of hiding and and controlling what happens with your data, you are in the end sending them through the internet, through the public internet. So security and privacy is something that you should take care of, right? And breaches happen from time to time. So yeah, if you want your data completely protected and secure, probably the cloud is not the best way to go. And then on number 8, which is also related with number 7, we have compliance. Many times there are some customers, there's some applications that we need to keep in a specific geographical area, for example, or to manage in a very specific way. So whenever we're dealing with sensitive data, there is this compliance where there are laws basically that we have to follow to control where our data is. So we might not be able to use the cloud for this or these other applications, right? So here, the cloud is also a little bit, it gives a little bit of trouble when it comes to managing where your data is stored. So all these are the problems that we think you are gonna encounter with the cloud, or probably you are already encountering at the cloud. But what is the solution? And as you can imagine, for us here at Barbara, the solution is the edge. So edge is the new cloud. If we quote what the guys at Gartner say, the ability to create results through AI and edge computing is the most significant value refactoring since cloud computing. And that's a high statement. But what is edge computing anyway? So what is all about this edge computing stuff? How is it different from the cloud? Well, the idea is that if we have our typical application where we have a device that we are doing things with that's connected to a router or an antenna, and that takes the connection to an internet provider through the internet and then to some cloud services. So say that we are operating in the cloud, chances are that we're gonna run into one or many of these problems that we just quoted, right? So the idea with edge computing is that rather than doing things in the internet, we tried to bring the computing power, we tried to do things closer to the place where all the data is being generated. So we try to bring it forward, ideally the closest we can to the place where the data is being generated, the closest to the device the possible. Ideally to a local network, right? So by computing our data, by putting all our workloads, all our machine learning algorithms, all our AI in a place that's close to the data, we're going to be overcoming all the problems that we spoke about a while ago. This is what we call edge computing. And we call it edge because we think that we are computing at the edge of the cloud. So if we think of this cloud of like a stain that covers a huge place, then we're computing it at the edge of that stain, so at the very border of the cloud. Okay, so that's edge computing, but what does it give to us? What's so good about edge computing? Well, here we have to speak about the edge computing drivers, and we have 4 main drivers here. The first being low latency. Remember that we spoke about latency before being a problem of the cloud? Well, edge computing doesn't have that problem because we're computing things very close to where the data is being generated and usually very close to where actions can be taken. So I don't know, we might be capturing data from a water management system. So if we need to open a valve or close a valve or do something in that system as a consequence of a piece of data that we have captured that says that there's a problem somewhere, then you could do that very, very quickly because you are computing very close to where the data originated, right? So this is key for real-time needs. Real-time applications can benefit a lot from edge computing. The second driver of edge computing is lower bandwidth consumption. Here we can go back to the example that we said before, where we have this computer vision system that we need to process in real time. So bringing all the camera feeds online onto the cloud is going to be very costly, and because it's going to take a lot of bandwidth, and you know that these cloud services are going to be invoicing us for all that usage of bandwidth. So if we do this in the edge, we're reducing dramatically the amount of data that we need to send to the cloud, right? So this will lower our cloud costs dramatically as well. So lower bandwidth consumption with edge computing. The third driver is privacy and security, because our data doesn't leave our premises. It's in devices that are very close to where the data is being generated. So ideally in our locations, in our offices, or in our manufacturing sites, or in, depending on the industry, we can call it different ways, but they are just locally to us. Then it's very easy for us to protect that data. If it doesn't leave the factory, then it's very difficult to get hacked. And then we have boost on autonomy and a boost on availability, because these systems, any edge computing system, is going to continue operating no matter if there's been a problem with the internet connection, no matter if the service in the cloud is broken, is unavailable. They have this autonomous system operation fashion to them, which is very nice for critical infrastructure, for critical industries that can't stop operating no matter what. So if we think of, smart grids or water management, then it's very nice that if they lose connection to the cloud, they continue operating, because these are high reliability sites. All right, but there are different types of edge, and if we look at the diagram here by Gartner, they usually depict this in 5 layers. So we have 5 different types of edge. At the top of the pyramid here, we have the cloud sort of services, and at the bottom we have the people and the things, right? So the site. And then depending on where we place our workloads, we will be speaking about a regional DC. So the cloud is like these huge data centers that are usually in the big cities. Here in Europe you might find them in London, Paris, in Frankfurt, or maybe Madrid. So the idea is that we move from those huge data centers to smaller data centers that we call regional data centers. We could move a little bit down to local data centers. So the idea is that you're going to be computing your workloads, your ML models, or whatever you're computing very close to your infrastructure, but you're going to be doing in someone else's rented infrastructure in a DC. If you go down, then you start to bring the computing power in-house. And here we arrive at the compute edge. So the idea here is that we have an edge server, usually locally, not in a data center, where you compute things, right? So we have compute edge, usually big servers. You have gateway edge, which is usually small machines, more portable sort of machines. And you have device edge, which is workloads that are being executed usually in embedded systems, so very, very small systems such as PLCs, wearables, small devices. The idea is, as you go down, you're going to get less latency, which is good if you're looking for a real-time system. You're going to be more scalable, and you're going to be more secure, right? So this is in line with what we just spoke about the drivers, the 4 big drivers of edge computing. Now, which of these edges is going to be the one that is going to have more business? Well, the idea here is, according to Gartner, that the lower you go, the better it's going to be in terms of business, which makes a lot of sense, because a regional DC is something very close to the cloud, or a local DC is something very similar to the cloud, right? So if you want to really get to enjoy all the good things about edge computing, then the further you are from the cloud, the more edge computing you're going to be doing. Then for those applications that really make sense in the edge, it's going to be better. So here we can see that gateway edge and device edge are probably the 2 that are going to make it in terms of being more used by companies. If we look to this impact radar by Gartner again, we can see that edge computing is usually at the center. And we can visit many of these diagrams, and we'll see edge in one of other fashion, appearing always very, very centralized. Here you have edge computing vision at just at the center of the radar, but you also have edge AI very close to it down there, edge AI, which is also an up-and-coming discipline. Okay, so this is our index today. We've gone already through the two first points. So what are the challenges of cloud computing and why the edge is for us a solution? Now we're going to jump on to point number 3, edge computing plus AI. And the idea is that we invite this new friend AI into the mix and see what happens, because edge computing is a very powerful technology, but when it couples with AI, then it just becomes a massive combination, a massive team. I'm going to see how we could do that. And for this, I've brought a couple of examples, real examples of projects that we've done with real companies here in Spain. And the first case is Acciona. This is a company that they do many, many things. In this case, we worked with the water management side of the company, and they usually manage many water treatment plants globally, and they usually spend a lot of money in chemicals because they have to ensure that the quality of the water is the best to be distributed. But when you put chemicals on the water to treat that water, usually you have to wait for some time because there's some dynamics there. It takes some time for the water to stabilize. So it is always a matter of trial and error. So you would just put some chemicals on the water, wait for a while, analyze it, then put some other chemicals on the water, wait for some time, analyze it. And there's this up and down sort of approaching the ideal level that takes a lot of time and also takes a lot of money because you might be using more chemicals than you should. So what they did is they come up with a predictive system where they would with machine learning predict the amount of chemicals that they would need from the start, right? So they would avoid this going for some bugs with adding more chemicals and retesting, right? And for that, they created a model that they trained with all the data that they had of past interactions, and they wanted to deploy it in the edge. Why does it make sense to deploy this in the edge? Well, because they have many water treatment plants globally. Each plant depends or belongs to a different company. They're very wary of data, so they want their data to be kept in the plant. So we have this privacy driver here, but also usually these algorithms are fine-tuned for each plant, right? So we have like this general model that gets fine-tuned down to the level of the sensor, right? And in one plant, they might have several sensors, 12, 20, 30 sensors. We have to train a model for each sensor. And you know that with time, those models come somehow decoupled from the sensors. So somehow, because we are using the model to predict things, we are somehow changing the environment, and then the sensors might not be as coupled to the environment, so we have to retrain the algorithm. Also, the sensors, they sort of change with time, so they change their capacities, they change their accuracies, they they get out of sync. So we have to retrain the models to make sure that they are relevant at that moment in time with that sensor. Obviously, you could do all this in the cloud, but probably it wouldn't make sense because you would be training many different models for specific devices down there in the cloud. It kind of makes more sense to have an edge device in the plant and train all those models locally. It's going to give you a faster throughput, and also it's going to be more careful in terms of data, right? So here we also have some of the other drivers that we spoke about that probably make the cloud not the best choice. So this is one of the cases that I bring you, but we have another one based on energy, and energy is especially these self-consumption markets that are emerging everywhere, but also smart grids, which is more of a medium-term bet, but it's something that's is gonna arrive as well. So in energy, we have loads of edge computing applications, because if you think of it, smart grids are usually highly distributed infrastructure, the critical infrastructure. So data and privacy and security is very important, but also autonomy. You need all those transformation centers or substations. You need them to work independently, but also it would be very nice if you could manage for them to talk to each other and somehow negotiate where should they route the energy through, so they ensure the best usage of energy, right? So we avoid throwing away energy on one side of the network while we are producing more energy that we need on the other side of the network, right? Just because we haven't routed it good enough. So if we could get all these nodes to speak to each other and find the best way to balance the network, that'd be great from a smart grids perspective. But the case that I bring you today is a case for EDP, and EDP wanted to work. They usually work in this autoconsumption space, and they wanted to give their customers at home a system that would allow them to make an intelligent use of the energy. So they will have these solar panels on top. They will have these batteries to get all the energy from the inverters. They will also have probably a charger for their electric car, and they will also be connected to the grid. So the idea will be here to make an intelligent use of the energy. So wherever we have available energy that's green energy, we should use that. But we should also maybe take care of when we charge our car or when we use our dishwasher or whatever. So the idea is that you make an intelligent use of all the energy, so you maximize the amount of renewable energy that you use at home. So this is a project, again, that makes sense in the edge, because we're speaking of many households. So you can imagine if you had to do in the cloud the computations for the models of each home, that'd be a mess. Also, we have here the problem of data and privacy. So it really makes sense to do it in the edge. So we created a system based on Barbara where they could do all this distribution of energy, intelligent distribution of energy internally in each home, using an ML algorithm to ensure the best usage of energy. The nice thing about this application is that it can also be taken one level up. So what if all the homes could speak to each other and somehow get in touch and exchange all the energy that they don't need anymore, or probably take turns to charge their cars, their electric cars. So I don't know, one charges from 10 p.m. to 11 p.m., then the next home charges from 11 p.m. to 12 p.m., and so on and so forth. So we would avoid a peak in consumption, and we'll have more of a distributed, flat usage of energy in a community, what we could call an energy community. So we can see many applications of edge computing in this space. This is one example, but you could see how it makes sense to run all those algorithms in the edge. Now, all these, the two examples I spoke about, they were very industrial, and that's because we at Barbara, we work in industrial edge computing. But I want to come back to a very sort of broad example that everyone knows, a more consumer example. I want to speak about Alexa, the smart speaker that many of us have at home. And the idea with Alexa is that there is some edge computing in play, but there's also some cloud computing in play. And I think this is a good example on how we will see edge computing complement cloud computing. So with Alexa, we have this flow here. We have a user, we have the device that's connected to our network, usually through the router, then it goes to the internet provider, and there are some services that are usually cloud services. So whenever the user speaks, Alexa takes the audio and digitalizes it, right? And here they use what they call a keyword spotting algorithm, which is it's a small algorithm that runs locally in the Alexa device, that is always looking for the keyword, in this case Alexa, right? So whenever it spots it, then it connects to the audio that's being spoken, so it could digitalize it and send the petition to the cloud. So here we have an ML algorithm running locally. So we could somehow speak of edge computing because we are running this algorithm in the edge, right? Then that audio that's captured is usually streamed towards the internet. And that's gonna fly over the internet, it's gonna travel through the internet, and it's gonna arrive at Amazon's server in the cloud. And the first thing that's gonna happen is the audio is gonna be converted into text. And that's gonna be done through a voice-to-text algorithm. So here we have an ML algorithm that's working in the cloud. Then that petition is going to get analyzed and a response is going to be prepared. And usually here, there might be other AIs that come into play. Again, these AIs are going to be executed in the cloud, right? So we saw how we started with an edge computing algorithm, and then that was somehow sent to the cloud for several cloud computing algorithms to come into play. Next steps would be preparing the response. Usually it's either a text or an action. If it's a text, it's going to get converted into audio. It's going to get streamed back through the internet to the device. And the audio is going to be converted in analog sound and it's going to be played back to the user. So the user gets the answer. Summarizing what has just happened is we've had a little bit of edge computing with this keyword spotting ML algorithm, and then we've had a lot of cloud computing with this voice and text conversion with these other AIs that come into play. So because most of the computation is done in the cloud, we tend to think that Alexa is a cloud computing solution, but truth is that there's a little bit of machine learning also going on locally in the edge, right? So this is in all if we are really truthful, this is a combination of edge plus cloud computing, right? And here I want to speak about this edge to cloud continuum, which for us is key, right? There's not a single application, probably there are, but there are many applications that make sense at some point between the cloud and the edge. So we don't think that there's like all cloud applications, or probably there's not all edge applications. Many applications, they need to distribute their workloads in this edge to cloud continuum. And we think that one of the most important things that you have to do when you're designing a system is trying to find in which place you're going to put this or that computation, right? So if you need low latency, if you need to protect your data, if you need to be autonomous, then probably you should put things on the edge, but that will probably be complemented with other things in the cloud that will give you some centralized point of view, that will give you some additional power of computation. So the idea is to work with this continuum and be intelligent about where you put your usually microservices. So, and here I have to take my words back just a little bit. So maybe the cloud is not broken. Maybe it just needs some friends. So maybe it just feels a little bit lonely. And edge computing is one of those friends that comes to the rescue. Probably the other big friend is AI, right? So if we combine these three guys, edge plus cloud plus AI, we have a very powerful team that's capable of almost anything. Almost anything. All right, so we've just seen how we should be deploying many models in different places from the edge to the cloud. How do we manage this complexity? I mean, if we have an application that's being deployed at several points, maybe we have a microservice running in the edge, maybe we have another microservice running in the cloud, maybe we have a microservice running somewhere in between in a local data center, or maybe we have an embedded part and then we have a gateway part. So how do we manage this complexity? Well, MLOps comes to the rescue. As you have imagined, it's all about MLOps. You know what MLOps mean? It's about maintaining machine learning models in production. so you could trust them and you can make sure that they're always there and doing their job. But the idea here is that we should be able to not only put them in production, but also monitor them and also keep collecting data and also retrain them and also redeploy them. And obviously that becomes a little bit messy when you're dealing with, I don't know, a deployment of 1,000 devices in the field. You might be used to do this in the cloud with a single model, or maybe with 10, 20 models, but models that are centralized in the cloud. You can imagine how messy that can come when you move to the edge and you have 1,000 devices, different devices in different locations. Some of them are very remote, so very difficult to reach. Well, that can become really a problem, and it's actually a problem. I mean, if you think of the challenges of MLOps according to AI Infrastructure Alliance, one of the biggest challenges that we have when we want to deploy models in the edge is that usually more companies than not take from 2 months to a year to put their models in production. So from the moment that they have everything validated, so they have the model, the model works, and they just want to put them in production, it takes up to a year, between 2 months and a year, for them to just deploy them, right? And that's especially due to the complexity of deploying models. Then one of the biggest MLOps challenges is usually deploying and also monitoring, right? If we're going to do this in the edge, well, we need a platform. We need, in the same way that if we're doing cloud computing, we tend to use a commercial platform. So we either go to AWS, or we go to Azure, or to Google, to whichever provider we like. We need a platform to do that also with edge computing. So that takes us to point number 4, architecture and frameworks. So here we have different providers, starting with traditional providers such as AWS. AWS provides you with basically anything that you would need. They are famous for not deprecating any service, so they have many services running and the stack is just huge. So if you wanted to do edge computing with AWS, chances are that you would be able to do it. We also have Azure, which is probably the other big contender in terms of traditional cloud platforms that go down to the edge. Again, there's a huge stack of products here. So if you wanted to use Azure, there's very high possibilities that you would end up being able to do whatever you want in the edge. However, there are some traditional players such as Google that are shutting down their IoT edge computing offering, right? So there's a little bit of confusion in the market where we have some big players that are betting on IoT and edge computing, and some others don't, right? And this is a recent news that they will be discontinuing that this year. We also have IBM, who have also retired their IoT cloud services. So again, there's a little bit of confusion here. It's not clear why they have decided to do that. Probably because it's so complex. Because the good thing about the cloud is that they managed to offer like a standardized horizontal sort of service. Whereas when we go down to the edge, it becomes a mess because you have many different devices with different hardware providers, different specs in remote locations. So that might have been a difficult problem to solve for these guys. The idea here to me is that these traditional cloud providers, they have seen the edge as a way to just go there and get data to pump their cloud services. So they're not native in the edge. They're more of someone that finds convenient to go to the edge to try and recruit some workloads, or to recruit some data that they can use to to bring customers onto their services online. Apart from these traditional guys, there's some native providers. These are usually new breed companies that have come alive, usually startups, usually in their 3 to 5 year of life, and they have come to life just to do edge computing. So their only objective is to do edge computing. So they are a different breed of companies in comparison to the big cloud providers, but they're also small, right? So we have Cedida, which is an American company. We have Crosser, we have Sunlight, we have Avasa, we have 6XQ, and we also have Barbara, right? And today I'm going to speak about Barbara because obviously that's the company I work in, and that's the platform I believe is going to become the new standard, but also because speaking about Barbara in a way means speaking about all the other guys, because we tend to do things in a similar fashion, give it or take, right? So if you think of the technological stack that you can find with these providers, you're gonna always find a different, flavor of this, more or less. So we can see in the right side of this slide that we have the stack divided in the cloud part and in the edge part that's below. The idea is that the cloud part is unique. We only have one cloud for all the edges, because the edge part is just thousands or tens of thousands, as many devices as you have in your deployment, right? And each of those boxes is one device in a remote location that's doing things autonomously, but is being managed by the cloud, right? So we usually have like a centralized point of view of all the decentralized distributed devices, right? And the way it works is as follows. In each device we have an OS. In our case it's Barbara OS. You could use usually any breed of Linux. If you think of Cedida, for example, they have Eve OS. It's their own operating system as well. And many other companies, they just use regular Ubuntu or Debian or any sort of open source distribution, right? So you have your OS at the bottom side of the device, right, which is controlling the underlying hardware. Then one step above that, you have what we call the Barbara Node Manager, and that's the name that we've given to it. But usually this is called an agent in some spaces, but what it really is a piece of software that's installed in the device and that manages all the connections and all the commands and the relationship of the device with the cloud motherboard, right? So sort of this centralized point where all the command and monitorization and all that should happen. So this node manager it's a small piece of software that runs internally and that ensures that anything that should be executed in the device gets executed, that anything important that's produced in the device gets communicated to the cloud, and that ensures that the system remains safe and working and autonomous and that everything's fine. That's the node manager. Then on the device we have also the workloads, and usually run inside Docker containers. I'm not going to go into what a Docker container is, but it's basically just a way of packaging applications, a very comfortable, convenient way of packaging applications. So we have there some purple workloads and also some white workloads, those small boxes that you find just there. The purple ones is because they usually run off the marketplace. We at Barbara, we have a marketplace where we offer pre-built and pre-tested and validated applications that the users can just deploy to their edge devices without having to program a single line of code. And then the white ones are the ones that users themselves can upload to the system, right? So you can either use pre-built applications and deploy them, or build your own applications and deploy them. So all that is happening in each separate device. Then when we come to the cloud, we usually have an API, so it's like the central point where all the commands are thrown, and that also receives all the monitoring feedback from all the devices. And then on top of that, we have what we call Barbara panel, which is just the front end. It's a visualization panel where you could see all the monitoring information, but also you could issue commands, right? So that's the architecture you're going to find in different providers. The idea is to manage different edge remotely located devices from a centralized point, but also maintaining them safe, maintaining them with low latency, maintaining them with being autonomous. So fulfilling every promise that the edge gives you, but also allowing you to control all those from a centralized cloud platform. All right, so let me show you an example of how these platforms work. In this case, we're going to log in into Barbara with my account, and you're going to see a list of devices that I have here. This is my demo account, so most of these devices are just for demonstration purposes, but the idea here is that you could have as many devices as you wanted, so you could have huge deployments in the thousands if you wanted to. And the idea is that you could group them by groups. So here I have 3 groups. You could have many more. Each group has several devices, and then you could also visualize them all together, or you could maybe also visualize them by groups. So I don't know, all the demo devices, or maybe all the AI nodes. I don't know, you could just browse through them. And for each device, you have to think that these devices, in this case, they are in our laboratory, in our offices in Madrid, but they could be just anywhere in the world, right? They could be in remote spaces running algorithms without even a connection to the internet, or just a very sketchy connection that comes on and off quite often, right? So the idea here is that you have all those devices and you could do things to them. You could operate them individually. So I don't know, I can go to this artificial vision edge node, and in this case we can see all the workloads that are being executed here. I could collapse all the cards, so all these light blue cards, they are apps that are being run in the device. In this case we have an image recognition model here. We could see the logs of that model and see how it's doing. But also there's other things running in there. We have a Grafana, that's a graphical interface. We have an influx that's storing all the data that is being read by the camera, but also all the data that's being produced by the model. Again, here you could also visualize the log and see what's going on in there. And you could easily remove things from here. So if I want to remove the model, I could just click on here and remove it. So I've deleted this card. It's going to disappear in a moment. Yeah, it's disappearing. Yeah, so it's gone. But now I could add it again. So sending workloads, machine learning algorithms, or anything to your edge devices is very easy. You just have to just select the app you want to send. In this case, we're going to be sending the algorithm. I don't know, I have the image recognition algorithm model, and then in this version I would just send it to the device. It should be shown in the same space that it was. So now we have it again, and it will be running in a moment. So the idea is that you could handle them individually, so you could ensure that your models, your visualization systems, your databases, anything is running on that particular device. So we are on this device that I have selected. But this could also be done massively. So if we go back to our nodes, we could do this in batch. So we could just select different devices. We could select the batch operation that we want to do, and we could just launch that. And we will be doing that for all those devices. So we could install a model in many different devices with just a couple of clicks. You could also update those models. You could also install other types of applications. So it's very handy when you have thousands of devices to be able to do that on batch. Then there's another view that's very interesting here, which is the spaces view, and that would allow us to see all the workloads that are running in our system, right? So application per application, model per model. So here we can see that in this case we have 3 image recognition models running in different devices. So one of them is running in this Edge Node VR, another one is running in the Artificial Vision Edge Node, which is the one that I showed. This is online, it's running at the moment. We could stop it if we wanted. We could just see the logs in a new screen. So this is a very neat and easy way to see all the workloads that you're running in the edge. So you have to imagine that this is not a cloud environment where you are running everything centrally. Each of these apps is going to be running in a different device, or maybe they're grouped into a specific device that's somewhere remotely. And the nice thing about this is that if they lose connection for some reason, they're going to keep on going and they're going to keep doing the magic that they're doing, right? So if they're routing traffic in a I don't know, if they're routing energy maybe in a smart grid, they're going to keep doing that. So they're very resilient to any problem with connections and with cloud systems. Point number 5 is about applications. We already spoke about 2 applications, if you remember, in the water management space and in the also in the smart grid, sort of auto consumption energy space. There are many more. I'm not going to go into them because I am running out of time, but you could check them out in our website, which is www.barbariot.com. There you have a section devoted to many different use cases, and you're going to see why it makes sense in these spaces to use edge computing. You're going to get some smart grids examples, you're going to get some smart water examples, also smart manufacturing, computer vision, and many, many more. So if you want to know more about what applications make sense in the edge, just go to our website. And we've reached the end of the presentation. I hope that you've liked it. I hope that it's been useful. If you need anything else from us, just please reach out. And I hope to see you soon at the next conference. Bye-bye.